Welcome. In today's video we're going to explore this very idea of interest, and in particular we're going to look at simple interest calculations. So what is interest? Well, when a lender provides an amount of money to a borrower, the lender obviously seeks some sort of return on the money that they've borrowed or that has been borrowed. Otherwise, what incentive do they have to give away their money? And this return that the lender receives is known as interest. Now, typically, an economic entity such as a bank or credit union will provide an individual with a sum of money on a given date, and then the individual will repay this debt with added interest after an agreed length of time. The financial transaction just described is what we call a loan. So the amount of interest will depend on three factors. One, it'll depend on the amount of money borrowed. It's going to depend on the length of the time that the amount is borrowed for. In other words, the time between the first initial date where the money is borrowed and when the money is repaid. That is what we call the length of time. And it will also depend on what we call this idea of the interest rate. So there are two types of interest rates or types of interest that we're going to encounter, and those are simple interest and compound interest. In this video we're going to purely focus on simple interest calculations and simple interest problems. So let's begin. So for simple interest calculations we're going to use the following notation. Now P, which we call the principal, is the sum of money that the lender initially gives to the borrower. I, which we're going to call the total interest, is the return that that lender receives for lending that money. And they get that interest at the end of the contract period. A, which is known as the amount, which we will call as the sum of the principal and interest. In other words, the lender gives the borrower a value of P at the beginning of the contract loan, and in return, the borrower gives the lender an amount A at the end of the term, which is equivalent to the sum of P and I. Now, R, which or lowercase r, we will denote as the rate of interest per period. Per period. It's important that we acknowledge per period. Now that per period, the period can mean half years, it can mean months, it can mean anything. But typically, with simple interest calculations, we're dealing with per annum, and per annum means per year. And of course, finally, T, which is the time in periods. So again, we usually deal with years for that particular case. But again, we can deal in a time period of months and so on and so forth. So for simple interest loans, the amount of interest I is given by the product of P, R, and T. In other words, the product of the principal, the interest rate, and the time in periods. The amount A, by definition, as we said, was the sum of the principal P and the interest I. So in other words, we can write A is equal to P plus I. However, we've already worked out an expression for I up the top here, and we know that I is equal to PRT. So we can replace that in the next equation here, and that gives us A is equal to P plus PRT. And finally, what I'm going to do here is I'm going to factor out that P, which gives us P or A is equal to 1 plus RT. Now, just to understand some terminology here for you, in that expression that we had in the previous slide, A is equal to P times 1 plus RT, A is called either the future value of P, or equivalently the accumulated value of P. This factor 1 plus RT, that's what we call the accumulation factor at simple interest. We'll also see what the accumulation factor at compound interest looks like, but for now we're just interested in simple interest. So that 1 plus RT, accumulation factor at simple interest. And the process of calculating A from P, the amount A from the principal P, is called accumulation at simple interest. Now, equivalently, if we took this expression here and we divided both sides by 1 plus RT, we could actually rewrite our equation by putting P as the subject. And by putting P as the subject, we have that it's the fraction A over 1 plus RT. Now here there's some new terminology that we're going to have to become familiar with. And here we call P the present value of A, or the discounted value of A, in fact. Now that factor, which is now the reciprocal of 1 plus RT, so that's 1 plus RT to the power of -1, or 1 over 1 plus RT, is what we call the discount factor at simple interest. And the process of calculating P from A is called discounting at simple interest. Now, I was talking about periods and the number of years, and I was talking about months, days, whatever. Now, it's one important thing to note here when we're doing these calculations. The interest rate R is usually expressed as a percentage per period. For example, we could say 10% per annum. But it's important to note that the measure of time we use corresponds with the rate of interest. And let me explain what that means in a little bit more detail. So for example, if you borrowed at a rate of say 10% per annum for a duration of 6 months, the value of R we could say was 10%, but the value of T would have to be a half. And how did I get half? Because it's 6 divided by 12. It's a half year. So the frequency of interest is per annum, which means per year, which means my value of time, T, needs to be in years. And 6 months is equivalent to half a year. So that's a key thing when we're doing these calculations. So always match the time with the frequency of interest. Let's go through an example now. Find the accumulated value of $10,000 for 10 years at a simple interest of 10% per annum. Quite nice, 10, 10, and 10. So in this example, we're told to find the accumulated value of $10,000. That means that the $10,000 is our principal amount. We're also told that there's an interest rate of 10% per annum. So what I've written here is R is equal to 10% per annum. And we're also told that it's over a 10-year period. So we can write T is equal to 10 years. Now in this case, notice that the years here, or the unit of time used to measure, time, is equivalent to the frequency here of interest per annum. And so we have no problem using T is equal to 10. So again, to find the accumulated value, we plug it into our formula that we derived previously, which said that A is equal to P times 1 plus RT. Substituting in our values, we've got P is equal to $10,000. We've still got the 1 from the 1 here. Now, in this case, what I recommend you do is you express interest rates as a decimal representation. So 10% in decimal form is 0.1. And the T here is equal to 10, as we said before. And then coming out altogether, that gives us a total of $20,000 as our accumulated value. Let's have a look at example 2 now. A loan shark is a money lender who charges extremely high rates of interest, typically under illegal conditions. Suppose a loan shark makes a loan of $200 to be repaid with $250 at the end of 1 month. What is the annual rate of interest? And I want you to take again notice of annual here. So in this example, what we have is a principal amount of $200, which then accumulates to $250. And again, because we're interested in the annual rate of interest, we've got to put our time in years. And 1 month, we're told 1 month is equivalent to 1/12 of a year. So I write t is equal to 1/12. Now we need to find the value of r. And to do that, we actually begin with the original, again, accumulation equation, which says a is equal to p plus 1, p times 1 plus rt. Now here what we're going to do is we're going to replace all our known variables in this equation with things we know. So example, we know a is 250, we know p is 200, and we know t is 12. So we're going to replace that all in the next part of the question. Here 250, 200, and here we've got our t is 1/12 times r. From here it becomes a matter of solving for r. So here's where the kind of financial mathematics ends and the algebra begins, the fun of the algebra. So what we can do here is divide both sides by 200, and that gives us, by dividing both sides by 200, that gives us 1.25 is equal to 1 plus r/12. Then taking 1 from both sides gives us 0.5 is equal to r/12. And finally, we can multiply both sides by 12, which gives us r is equal to 3, or in percentage terms, remember, that is equivalent to 300%. Okay. 73 days, again, we're going to go through a third example here. 73 days after borrowing money, a company pays back exactly $204,000. How much was borrowed if the $204,000 payment includes the principal and the simple interest at 10% per annum? In other words, what we're really told here is that $204,000 payment is the accumulated value. So again, we've got A is 204,000. We've got a rate of 10% per annum. But here again, we've got 73 days, but we want to convert 73 days into years because again, our frequency of interest is per annum. So what we do here is we take 73 on 365, which is 1/5 of a year. Again, that simplifies down to 1/5. Again, 365 days in a year. So then what we can do is we can actually use the formula we derived previously, which made P the subject. So P is equal to A over 1 plus RT. Then we substitute in our values. Here we've got 204,000. You've got R is 0.1. Again, I've replaced 10% with 0.1 and T with 1/5. And that comes out to be 200,000. So that was the amount that was borrowed. In other words, P, the principal, is the amount that was borrowed. So finally in this video, I'd like to just quickly talk about the time between dates. So in most simple interest calculations, it's important to know the exact number of days between the time of lending and the time of repayment. And so when we work out the number of days, it's important for consistency's sake is that we include the day the money is lent. Sorry, we exclude the day the money is lent, but include the day the money is repaid or withdrawn. And I'll explain more so in the next example. But again, what we're going to need to know, and you'll need to memorize these particular values here, is we need to know the exact number of days for each month. So for example, in January, there are 31 days. In March, there are 31 days. April, there are 30 days. And remember, in a leap year, February has 29 days, but in a non-leap year, it only has 28. And of course, you've got to go through all this whole table to be able to calculate the number of days between exact dates. So, finally, to conclude in this video, we're going to look at a calculation that involves finding the number of dates between the 21st of February and the 4th of May in 2020. So 2020 is a leap year. Now, by the way, to know that a year is a particular leap year, you need to know that it's divisible by 4. So 2020 is divisible by 4, and therefore it is a leap year. So here we're going to begin by drawing a timeline of the situation. So here we've got that 21st of Feb that we were talking about, where the first part of the day. And then what I do each subsequent in this timeline, I put in the end of each subsequent month. So first I put in the 29th of Feb as the end of Feb. Then I put the 31st of March as the next date, and then the 30th of April as the next date, end date of the next month after that. And then finally, again, remember we're talking about the 4th of May, so that's what we're interested in here. So between the 21st of Feb and the 29th of Feb, you'll notice that there are 8 days. To see that there are 8 days, simply what you have to do is take 29 minus 21. That gives you your 8 days. Again, we don't include the 21st of Feb, so that would be including the 22nd, 23rd, 24th, 25th, 26th, 27th, 28th, and 29th is 8 days. Then, in the next month, we have to include the 31 days in March, so that's why I've put 31 days here. Then for April, in the April period, we've got 30 days, as you can see, because there are only 30 days in April. And finally, we have to add on those initial 4 days that we were talking about in May. And so finally, we can say that the number of days is 8 plus 31 plus 30 plus 4, which turns out to be 73.